Good afternoon, everyone. My name is Tom Lendacky. I work at AMD, and we're going to talk about secure encrypted virtualization and what we're currently working on for improvements and where we're going with it. For the agenda, I'm going to give a quick overview, quick review of SEV in general. I'm going to talk about live migration, which just kind of came up in the last presentation a little bit, what we're doing for live migration, and then this concept of a migration helper, and then some of the performance work we're doing around SEV. Then I'll move on to SEV-ES and give kind of another review of that and where we stand on the submission upstream. It's more of a status overview for SEV-ES. And then very, very brief mention on the next evolution in SEV called SNP, or Secure Nested Paging. For a quick review, the idea is that SEV protects VMs and containers in VMs from other VMs, from administrator tampering, and from untrusted hypervisors through encryption isolation. We have one key for the hypervisor, and then we have one key for each VM, and that allows us to cryptographically isolate the hypervisor from the VMs and from each VM to other VMs. So this all integrates with our existing virtualization technology. You can continue to run standard VMs alongside SEV and SEV-ES VMs. So one of the areas that we're working on is SEV live migration. Right now, the existing SEV support doesn't support live migration. Because the hypervisor can't just move or copy a page from one machine to another machine. And that's for two reasons. One, the encryption key that's associated with the source machine isn't migrated to the destination machine. You get a different key as soon as the VMs start up, and so that would cause the ciphertext to become all distorted. The other reason is even if you could migrate those keys, the physical location of the page in memory makes a difference. So while the guest can see a page of zeros at one address as a page of zeros at another address, from the hypervisor's point of view, he sees two different ciphertexts. So if you were to move that page from one machine to another machine, and it's not in the exact same physical location that it was on the source machine, then nothing will work. So given that, we have to use the SEV firmware to move the pages, right? And what we do is have the source and destination machines negotiate some transport keys, and those transport keys are then used to wrap the data and send it from the source over to the destination. Destination machine then unwraps the data, and we've migrated the page. Now, one of the things we need to know, and this is part of the support that my colleague back in Austin has submitted upstream for QMU and for KVM support, is we need to know what pages are actually encrypted, because you don't want to try and decrypt a page that isn't encrypted. So we're introducing a hypercall from the guest, so whenever we change the encryption state of a page, the hypervisor will be made aware of that, and we'll know when a page is encrypted or not encrypted and what we need to do appropriately. There'll be updates made to QMU so that when we see an encrypted page, we'll call down into the kernel, then call into the SEV firmware, use the SEV APIs to then wrap that page for transport across the line. And then there's metadata associated with that information as it goes across the wire to the destination machine. We'll use receive APIs to then unwrap it and put it into the guest on the destination machine. At the end of the full migration, that guest page encryption state is one of the last things sent, so that the guest on that side now knows the state of everything, and it could then be migrated yet again if it needs to. So the problem comes up that we have to use the secure processor to move all these pages. And the secure processor was never intended to handle a stream of megabytes or gigabytes of data in a performant manner. So it becomes a bottleneck. So we started thinking about what we could do, and you can think of migration being broken down, and SEV migration being broken down into two phases. You have an authentication phase where the AMD secure processor would be used to enforce guest policy on migration, whether or not to even allow migration is part of the policy, right? And then a data movement phase. And the data movement phase is where this migration helper comes in, right? It's currently a proof of concept that we have. You can think of it almost as a hidden vCPU, but it's basically an AMD's talk VMCB that represents something that can be run through a VM run instruction. It would run only the migration code, and the migration code is very small, kind of does three things. It initializes a key for migration, it can encrypt pages and decrypt pages. So if we look at how this would work, what we would need to do is we use the send APIs, the SEV firmware, to migrate the migration helper first, right? It's very small, so we can get that sent without, having a bottleneck with the processor, the secure processor. The destination hypervisor would then receive that migration helper. The migration helper will have done an init, so the key is now transferred from the source to the destination. And then you now have the migration helper running on both machines, and you would then start calling, instead of the secure processor, you call into the migration helper, which would be doing CPU, x86 CPU instructions to migrate the page, right? So we could use AES and do like AES GCM so that you can get the encryption and integrity support. And instead of migrating at megabits a second, we're now able to migrate at gigabits a second. So that was migration, and moving on to just performance in general. One of the other things about SEV is we have to pin all of the guest memory, right? As I mentioned in migration, right, physical location matters, so we can't have the hypervisor moving the pages around, and because we would just run into issues when we tried to decrypt those pages. The problem with pinning memory is you have higher initial resources, requirements associated with startup, and depending on the size of the VM, right, you have a slower startup as you're pinning all this memory. So we're investigating a few options. One of the first ones we're looking at is to just prevent page migration for an SEV guest. We either will mark the page as an SEV guest page or determine that the page is somehow related to an SEV guest and just prevent the page from being migrated. That would eliminate the need to have to pin the memory and therefore get kind of a quicker startup. The other option is we have newer firmware support that can kind of do a copy. So if you really want to rebalance your memory across NUMA nodes or things like that, we can make use of that, where we can hook into the page migration or compaction and swap paths determine based on the same bitmap that we would use for live migration as to whether or not a page is encrypted or not, determine whether we need to use this copy API, and then we could move the page through the SEB firmware. We still don't have any support for or an API for swapping, and that's one of the other things we're going to be continuing to look at is swapping support. Another area of performance work that we looked at, and these patches were accepted recently and will be in the 5.5 kernel, but it deals with our ACID activation. So in our first generation of EPIC machines, we supported 15 concurrent SEV ACIDs. In our second generation, we bumped that from 15 to 509. So you can have 509 guests running. Our maximum thread count is 256, so you can pretty much run concurrently while all the guests on the box full time. But what we were doing previously was, in order to ensure that we don't get any kind of cache corruption or things like that, when we go to reuse ACIDs, we would have to do a write back and validate across all the CPUs, followed by a DF flush. These are very, very expensive operations. So you can see from the diagram, we would find an available ACID, we'd perform this write back and validate, DF flush, do an activate, and at that point we would launch the guest. The guest could run for a while, do whatever it needs to do, but when the guest shut down, we'd then do a deactivate, followed by another write back and validate DF flush, and then put that ACID back in the available ACID bitmap. So the change was to now track these ACIDs that we deactivate as reclaimable ACIDs. So we start with our available ACIDs. The guest will get a free available ACID. We'll just do an activate. The guest can run. When it shuts down, we do a deactivate, and we free the ACID into the reclaimable bitmap. Now, the next time a guest starts, so we could do this on our newer machines, 509 times. When you get to 510, there would be no more available ACIDs. We'd go down, we'd do a write back and validate, DF flush, and that would cover all of the ACIDs that have been freed up to that point. So we would take all the reclaimable ACIDs, put them back into the available ACIDs, then continue on. So we reduce the performance impact associated with that dramatically by doing that. Moving on to SEV-ES, quick overview. We build on SEV through guest register state protection. So the guest register state becomes encrypted. It's initialized to a known state, then it's measured and encrypted and measured as part of the launch process. An integrity check is performed whenever we do a VM run with SEV-ES. And the VM run would fail if the hypervisor tried to alter that register state. And then world switches currently now swap all register state. The VM control block under SEV-ES changes. So where we used to have one page that had the control area and the save area integrated, that now gets split. So the control area now points to the save area, and that save area is a page on its own, and that's what gets encrypted and measured. It's also been expanded to save more state. So it uses a little bit more of that 4K page, but it's nothing dramatic in the size of memory that has been now used. We also have what we call a guest hypervisor communication block to allow the guest and the hypervisor to communicate any state needed to perform some functions for the guest. For example, MMIO or MSR reads and writes, CPU ID instruction, that type of thing. It's a shared page between the hypervisor and the guest, so it's unencrypted. And there's a specification that documents it all and some of the protocols around how we do guest startup and how we run under SEV-ES. So from a current status, I talked about SEV-ES last year, and you can look at that presentation to kind of see what we're doing. But from the current status, the protocol specification is just about final. I'm adding just some final CPU ID and MSR requirements that the guest expects to be set. The OVMF patches or EDK2 patches were recently submitted in RFC, in the process of taking all those comments in and submitting the third version of those. Kernel batches are still being completed. There's some things like early exception handling that we have to work on, some NMI handling, things like that to finish that out. But then hopefully we'll get those submitted quickly. QMU patches, I have a working QMU, but there's still some things to investigate there as far as how QMU does register accesses. Right now it just says, give me all the registers. We don't supply all those registers on exit. You only supply what registers are required. So we have to look at how we go about doing that. We have a GitHub tree with the QMU, OVMF, and kernel patches available. So they can be applied and run on both our Naples and our Rome system, or our first and second generation EPIC systems. The next step, and this is kind of a plug for another colleague who will be presenting secure nested paging tomorrow at the Linux Security Summit. This is the secure nested paging is our next step in evolution of SEV, where SEV provided the confidentiality through encryption of memory and then encryption of register state. SMP is going to build on that and add integrity protection. So this is going to help guard against replay attacks, corruption attacks, remapping attacks, make sure that when a guest writes a value to a page, it's guaranteed to read that value back. So some nice added things there from an integrity protection point of view. Like I said, David will be talking about that tomorrow. We'll have a white paper out on that very soon on our SEV site. So if you go to developer.amd.com/SEV, and that reference is on the next page on the list of references that I have. But that paper should hopefully be out tomorrow. So it would be good to read. If not tomorrow, it'll be very soon after that, just working through all the details to get that all posted. Here's the list of references. Just added that so that you can do that later. Disclaimer, done. So that's pretty much it. Is there any questions on anything?
I just wondered, how does the migration helper communicate with the QMU migration process?
So the QMU migration process is updated so that it knows about the encryption bit mask, and if it sees that it's an SEV guest with an encrypted page, it'll call down to the kernel, right? And instead of going to the SEV API to have the page wrapped, it'll issue basically a VM run into this hidden vCPU, which is the migration helper. That will encrypt the page using x86 instructions. It's a lot faster. The page will be wrapped and placed into a shared memory area that the hypervisor can use. It'll pass that back up to QMU, and that's what QMU will send.
Sorry. I just occurred to me, like while thinking about all the SEV stuff, what do you do on UEFI runtime services?
So the migration helper is actually, we're thinking probably would best live in
outside of
UEFI.
migration, just in a normal SEV enclave, you have UEFI runtime services that are provided by the host environment, right? So I, as a hypervisor, provide firmware into my guest, which then lives on inside of my own context that is running with secure everything enabled. So if I take a random operating system today and this is a general purpose SEV question. If I take my normal OS and I just have UEFI runtime services pulled in, doesn't that mean that I can essentially read out all that secure data from inside that guest? I think Liran wants to answer it. But.
I'm trying to follow the question.
So I think the question is that because the hypervisor is the one that actually provides what is the OVMF firmware, it can also define what are the UEFI runtime services that are called inside the guest. And therefore, if I enter a malicious runtime service, it can provide me the data, for example, using hypercores or things like that. But
Right,
I think yeah, go ahead.
So the UEFI is measured at launch. So as long as you have vetted that code and know that you don't have anything malicious in there that's just going to pump out data, right? You know, it becomes something that's measured. You could validate that measurement, and if the measurement doesn't match, and this goes back to SEV in general and how we do launching of guests, right? The guest owner can look at that launch measurement and decide whether or not to continue the boot of the guest. So that would be a way for it to detect whether somebody has inserted a malicious UEFI or not.
I think that in general it's just an orthogonal problem that even in standard PCs, you are afraid that the runtime services are malicious. So like you said, you can either measure them, or for example, in other cases, like in Windows, for example, in VBS, they isolate them, like put them in VTL 0, for example. So it's just orthogonal to the MD7 architecture in general. But I have a different question. You said that the the firmware that actually does the encryption doesn't do it fast enough like an x86, right? But if I don't consider migration for a moment, isn't this exact same firmware used for doing the encryption of the guest memory pages in general?
No. So the SEV firmware does the initial encryption of like the UEFI blob, but after that, anything that when a page is loaded and written, it's going through the UMC, right? So the SEV firmware actually routes stuff through the memory controller, right? And the memory controller is the one that's doing the actual encryption. So whenever you read or write to memory, it will, assuming that you have set the encryption bit in the guest, then it'll go through the encryption controller and the memory controller, which is...
Exactly. So one question that it raised for me is why can't the only thing that needs to happen is to re-encrypt the memory page with a different key that was negotiated through the migration channel, right? Now, why can't the SP firmware just, because it knows the original key of the guest, it can read the memory through the memory controller and then write through the memory controller with the new key that is now the transport key that used in the encryption of the new key that now I can send the migration pages. Like use the existing MCH.
If I understand, you're like saying like put in a second key and
what I'm suggesting is that the SP firmware will just install the new transport key inside the MCH, like you do for standard SEV keys, and then you read through the previous key to get the data, and then write through the new page that is now installed with the transport key. And now you got the plain text encrypted with the transport key that is ready for being transmitted.
I'll have to talk to you after this about what you're trying to get at. I'm not quite sure where the transport key, how we're going to inject that into the memory controller. So Well, I mean, the transport key would, yeah, it would almost need like, we'd need to double the key space in
Yeah.
order and so now you're limiting the number of guests that you can have, and the UMC is still going to be doing the same encryption methods, so you still have the tweak involved that would render it not usable if you put it in a different location.
Can I interrupt here? 'Cause I'm David Kaplan. I'm also from AMD. The issue is less about the encryption bandwidth. It's about the latency between the hypervisor and the security processor. So because we typically encrypt one page at a time, it's going out to there, waiting for the interrupt to come back. There's a very long latency there. There is fixed function hardware for doing the encryption. That's a very tiny piece of it. By doing all the operations in the x86 and the migration helper, it cuts down on the latency significantly. Does that make sense? Yes. Yeah, so the question is the latency about the time between the hypervisor and the security processor? Yes, because the security processor looks like a PCI device, so you're going out, it's like microseconds, right, to do that.
Okay, thank you.